Hello viewers, it is indeed a great pleasure for me to bring to you another program in the Teleschool Senior Series. The subject today is functions. As it is an important one, we have devoted 2 programs to this topic. In this first part, we are going to look at function, its definition, the vertical line test, 1-1 function, the horizontal line test, and some analytical methods. So let's start with a very simple problem. An apple costs 2 rupees. What is the cost of 2 apples, 3 apples, 4 apples, and 5 apples? Of course, you know the answers. It is very simple to calculate. 1 apple costs 2 rupees, therefore 2 apples would cost 4. 3 apples would cost 6 rupees, 4 apples would cost 8, 5 apples would cost 10 rupees. We can use set notation to present the solutions. Let's see. Number of apple costs. 1 apple would cost 2 rupees, 2 apples 4, 3 would cost 6 rupees, 4, 8, 5, 10, and we can write it in this form. Now, we can also use some other variables to represent this relationship between number of apples and the cost. For example, number of apples can be represented by x and cost of x apples by f, which would give us 2x. This means that cost depends on x, that is, cost is a function of x. In fact, fx is equal to 2x. We will say that f is a function from set of number of apples to set of costs. So this is another way of representing the same information, with number of apples represented by x and the cost by f. So this simple problem has been converted into functions. That is, f is the cost which depends on the number of apples. So fx is equal to 2x because 2 rupees is the cost of 1 apple. We can use the function notation to calculate the cost of other number of apples. Fx equal to 2x, therefore cost of 10 apples means x equal to 10. F of 10 is 2 times 10, 20 rupees. X equal to 15, f of 15 equal to 30. So once we have written what the function is, like here, fx, which is the cost, is equal to 2x, we can use it to calculate other costs. Let's now define what a function is, using the proper variables and the sets. Suppose that we have a function f from set A to set B, written as a function f from A to B. It is defined as a rule which associates each element x of the set A, one and only one element of B. So we have set A, set B. F is a function from set A to set B. Function f must associate with each element of the set A one and only one element of set B. So only one and only one element of set B is associated with each element of set A. The element of set B is usually represented by fx. Associated with functions, there are other important sets which we will define now. f is a function from set A to set B. Fx is called the image of x. Set A itself is called the domain of the function f. Set B is called the codomain of the function f. The set of images is called range of f. So the set A would be referred to as the domain, set B the codomain. Fx itself is an image. The set of images would be referred to as the range of the function. So these are the variables, the sets that we will use. We also refer to x as the independent variable and fx as the dependent variable. We will now consider a few examples. We'll see together whether the relationships are functions or they are not functions. So, consider a function f from set A to set B. Is f a function? No. All the elements of set A have been associated with elements of set B, and each one from set A has been associated to only one element in set B. So we'll say yes, it is a function because every element of set A is mapped onto a unique element of set B. Similarly, what is the domain of the function f? It consists of the elements 1, 2, and 3. What is the codomain of the function? Codomain is contain the elements 1, 4, and 9. And since these elements themselves are the images, then we will say here the codomain is same as the range, and it contains the elements 1, 4, and 9. 1, 4, and 9. Let's take another example of a relationship, and we'll see whether it is a function. Consider a function f from set A to set B. Is f a function? We know that in the domain, the element 3 doesn't have an image. 1 has been associated with 1, 2 from the domain has been associated with 5, but 3 does not have an image under the function f. Therefore, f is not a function because element 3 of set A has not been mapped onto any image. There is no image associated with 3. So there is no question of domain and codomain here, since f is not a function. We'll take another example. A function f from set A to set B, defined as follows. Is f a function? We know that element 2 has been associated with 3 in set B, but element 1 has been associated to 2 elements in the codomain. Therefore, we conclude that no, f is not a function because element 1 has 2 images. We'll take one more example. Again, consider a function f from set A to set B, defined as follows. Is f a function? Note that all the elements in domain have each one an image. And each one has only one image. One is associated to 4 only, 2 is associated to 4 only, 3 is associated to 5 only. There is no element in the domain having 2 images. Of course, element 1 and 2 have the same image, but no one has 2 images. So yes, f is a function and its domain consists of the elements 1, 2 and 3. The codomain consists of 4, 5 and 6, but the range is only the set of images. It consists of elements 4 and 5 only. So here f is a function with domain 1, 2 and 3, codomain 4, 5 and 6, but range 4 and 5 only. There are certain very popular domains which you will often see. So let's see the popular domains. R is used to represent the set of real numbers. R plus the set of all positive real numbers. Similarly, R minus would represent the set of all positive, of all negative real numbers. Z represents the set of integers. There are different ways in which we can represent a function. We have seen you can use sets. You can also use the notation fx equal to 2x. So we'll see some other ways. Fx equal to 2x was one of them, and fx, f maps x onto 2x, where x comes from the set of real numbers. So either we write it like fx equal to 2x with the domain described here, the set of real numbers, or f is a function which maps x onto 2x. We can also refer to x as the input to the function f and 2x as the output of the function. So f is the name. We could have other names, g, h, I, any other name can be used. So in all definitions, we must have the name of the function, the input, which we call the independent variable, the output, which is the dependent, and we also have the domain and the set of images called the range. It is very common to associate functions with graphs. So let's take an example. Fx is equal to 2x, and x is a real number from -2 to 3. That is, the domain is from -2 to 3. Let's draw the graph of the function. The x-axis, the vertical axis is the fx axis, the domain from -2 to 3. Fx represents a straight line, fx equal to 2x. And you will agree with me that the range in that case would be by replacing -2, 2 times -2, -4, 3 times 2 is 6. So the domain would be from -2 to 3, and the range from -4 to 6. So we can show the domain and the range of a function using graphs as well. The domain would be usually represented by the x coordinates, whereas the range by y coordinates. So we can use y coordinates to represent the value of fx, and then we can write y is equal to 2x, the domain -2 to 3, and the range as fx lying between -4 to 6, and y between -4 to 6. So either we write y or fx when we are associating a function with its graph. Now we will consider the vertical line test. Whenever we have drawn the graph of a function, we can use the vertical line test to verify whether the function, whether the relationship itself is a function or not. Let's consider the function fx equal to x squared, where the domain consists of all real values. So fx is equal to x squared. And we'll see whether this relationship is a function or not. So we draw the graph. Of fx equal to x squared or y equal to x squared. The vertical line says that each vertical line should not cross the graph of the function more than once. So after drawing the graph, we'll draw vertical lines. We find that all the vertical lines cross the graph once only, which means that yes, f is a function. So vertical line test allows us to verify whether a relationship is a function or not. By drawing the graph and then drawing the vertical line, we verify that no vertical line must cut the graph more than once. And then we conclude that the relationship is a function. Let's consider another relationship. Fx equal to plus minus square root of x. And the domain here consists of all positive real numbers, including 0. If we draw the graph of the function fx, then this is the shape that we'll see. In order to verify whether fx is a function, we should be drawing vertical lines. We find that the vertical lines are crossing the graph more than once. In fact, they're crossing the graph at 2 points, and we conclude therefore that fx is not a function, because there are vertical lines crossing the graph at more than 1 point. It is a common mistake as well to associate endpoints of the domain with endpoints of the range. Very often, students make this mistake of saying, well, if the domain would range from, say, -2 to 3, then the corresponding values of fx, that is, values of fx corresponding to -2 and 3, the endpoints of the domain, would produce the range. In fact, this is not always the case. We'll take an example to illustrate that. If we consider the function fx equal to x squared plus 5, with values of x ranging from -2 to 4, we found that the shape of this graph is a quadratic. That is, it is a parabola. The domain is from -2 to 4. The graph is a parabola. The minimum value of fx is 5. Therefore, the range is from 5 to 21. Now, let's look at the endpoints. That is, let's look at what is the value of fx when x equal to -2. It is 9. When x equal to 4, the value of fx is 21. So, associating range to the endpoints would have produced a range from 9 to 21 instead of 5 to 21. Therefore, here the range is fx lies between 5 and 21, and we conclude that endpoints of the domain do not necessarily give endpoints of the range. So, whenever you are asked to find the range of a function, you must be very careful, because calculating the endpoints of the range from endpoints of the domain may not always produce the right range. So to calculate the range, it is advisable to draw the graph and see what is the minimum and what is the maximum value of fx. These minimum and maximum values would give you the endpoints of the range. There is another special type of function that we need. It is called the 1-1 or 1-to-1 function. Let's define a 1-to-1 function. A function f from set A to set B is said to be 1-to-1 if images of distinct points, that is two different points in set A, under the function f are distinct points of B. That is, no two elements of set A must have the same image in set B. Let's take an example. F is a function and f is 1-1 because no two elements of the domain have the same image. Let's take another example. G is a function, but G is not a 1-to-1 function because two elements of the domain have the same image. So G is not a function, but f is. There is a test called the horizontal line test, which can be used whenever the graph associated with the function has been drawn. So if you are drawing the graph of the function, then it's better to use the horizontal line test to test whether the function would be 1-to-1 or not. Let's take an example. Consider the function fx equal to 2x. The graph is a straight line passing through the origin. We would like to know whether this function is a 1-to-1 function or not. So we are going to draw horizontal lines. The horizontal lines must not cut the graph of the function more than once for the relationship to be, or the function to be, a 1-to-1 function. So if horizontal lines cut the graph at more than one place, then the function is not a 1-to-1. Here, fx equal to 2x is a function. We will now apply the horizontal line test to another function, fx equal to x squared, the quadratic. And you know that the graph of fx equal to x squared is a parabola. So fx equal to x squared, the graph is a parabola. We want to know whether this function is a 1-to-1 function or not. We are drawing horizontal lines. As you can note that the horizontal lines are cutting the graph at 2 points. Even if others do not cut the graph, you have at least one horizontal line which is cutting the graph of the function at 2 points. It is sufficient to conclude that fx is not 1-to-1 function. It is a function, yes, but it is not 1-to-1 function. We can also use analytical methods to prove whether a function is 1-to-1 or not. We will now consider the function fx equal to 3x plus 2 and apply the analytical method. fx equal to 3x plus 2. The domain is the set of all real numbers. So fx equal to 3x plus 2, the graph is a straight line, and it is from the set of real numbers to the set of real numbers. Now, to prove whether the function is 1, 1 or not, we're going to start by saying let fx1 equal to fx2, which means 3x plus 1 3x1 plus 2 equal to 3x2 plus 2. And from that we can conclude x1 equal to x2. That is, if two different images have the same value, then they must correspond to the same element in the domain. fx1 equal to fx2 must necessarily imply x1 equal to x2. Again, horizontal line test would again reveal that yes, fx is 1 to 1. We have seen the function fx equal to x squared, and applying the horizontal line test, we saw that fx equal to x squared is not 1 to 1 because horizontal lines were cutting the graph at 2 points. We're going to apply the analytical methods to prove that fx equal to x squared for the domain x equal to r is not a 1 to 1 function. Fx equal to x squared, the domain is the set of all real numbers. We have seen the graph, and fx using the horizontal line test was shown not to be 1 to 1. Now, we are applying the analytical method. We start by saying let fx1 equal to fx2. So x1 to the square will be equal to x2 to the square, from which x1 is equal to plus minus x2. So we find that x1 is equal to x2, or x1 can also be equal to minus 2. So which means that there are two elements of the domain, x2 and minus x2, which have the same image. Therefore, fx is not 1 to 1. We will now consider continuous functions. Let's define continuous functions. Continuous function refers to function continuous within their domain. We'll take two examples. Fx equal to x squared is a function. If we restrict the domain from minus 2 to 3, we'll say that yes, fx is continuous in the domain minus 2 to 3. If we consider another function, we found that there is a jump here. Fx equal to 0 for all negative values of x, and fx equal to 1 for all values greater than 0. So we conclude that fx is not continuous because there is a jump in the function at x equal to 0. Yet another important type of function is the increasing function. We have seen 1 to 1 function, we have seen continuous function, now we'll see increasing function. Consider this function y is equal to fx in the domain a to b. We see that fx rises. Fx is rising, which indicates an increasing function. So we say that fx is an increasing function in the domain a to b. Now, let's define increasing function. Let x1 and x2 be two elements of the domain D, such that x2 is greater than x1, and fx is continuous in that domain. We will say that fx is increasing if fx2 is greater than fx1. So, if x2 and x1 are two elements of the domain, fx2 must be greater than fx1 for fx to be an increasing function. We're going to show it on the graph. If x2 is greater than x1, then fx2 is greater than fx1. Then we'll conclude that fx is increasing. x2 is greater than x1, fx2 is greater than fx1, and we conclude that yes, fx is an increasing function. There is a derivative condition which allows us to verify again whether a function is increasing or not. Let's see the derivative condition. If fx is continuous within the domain D, and f dash x, that is the derivative of fx, is greater than 0, that is positive for all x in D, then fx will be said to be an increasing function. Now, let's consider the function fx equal to x squared. So, the domain consists of all real numbers. Is fx a continuous function for all values of x? Of course, you would say no, because fx would be increasing for all positive values and it would be decreasing for all negative values. Fx rises only for positive values of x. Let's see on a graph. That's only one part of fx equal to x squared. Let's consider x1 and x2. Clearly x2 is greater than x1, and we find that fx2 is greater than fx1, and fx rises. Therefore, fx is increasing only if x is positive. We'll apply the derivative test on the function fx. So from here, x2 is greater than x1, fx2 is greater than fx1, which means that fx is increasing only if x is greater than 0. Now, fx is equal to x squared. We'll apply the derivative test to show that fx is increasing only if x is greater than 0. Fx equal to x squared, so f dash x is 2x. That is, if we differentiate fx with respect to x, we obtain 2x. You will agree with me that 2x can only be positive if x is greater than 0. So the derivative would be positive only if x is greater than 0. From this, we conclude that fx is increasing only if x is greater than 0. So viewers, this brings us to the end of today's program on function. In this program, we have defined what is a function. We have considered the vertical line test, the horizontal line test, one-to-one function, increasing function. We hope that you have enjoyed watching this program. Until next time, it's goodbye from us.